In this lecture, we continue our introduction to the mesh current method for determining currents and voltages in a circuit, and we show how to use this method for a circuit that contains both independent voltage and current sources. Well, here's a circuit that has two voltage sources, three resistors, and one current source. Now, if we identify three mesh currents within this circuit, so let's call this mesh current I1. We'll call this one I2, and we'll call this one I3. And then, of course, if we wanted the current that flows through this 4 kilo ohm resistor, that would be from top to bottom, that would be I1 minus I2. The current that flows from bottom to top through this 8 kilo ohm resistor, that would be I3 minus I2. So if we want to solve for these three mesh currents, we could write three mesh current equations and then systematically solve for those. Now, of course, as we write through this first mesh, we should know what to do now. We'd write a minus 4, and then 2,000 times I1, 4,000 times I1 minus I2. We could write an equation for this mesh, but when we get to this mesh, we'll know how to write an equation for the voltage drop through the resistor, but how do we write an equation for the voltage drop across this 2 milliamp current source? Now, again, for the voltage sources, the voltage drop is determined by the value of the source. For the resistors, the voltage drop is determined by Ohm's law. But we don't have a direct way to write an expression for the voltage drop across this current source, so it might seem like we're having a little trouble applying this method. However, we don't need to do that because this current source is in a location that gives us a direct solution for one of our mesh currents. That is, in this case, the mesh current I3 is flowing downward through this wire in the opposite direction of this 2 milliamp current source. So from inspection, if we just look at this current source, that tells us the value for I3. And I3 then is equal to negative 2 milliamps. Now we can write the mesh equations for the other meshes, and when we encounter an equation that involves I3, we'll just substitute the value of negative 2 milliamps. So let's write the equation for this first loop. Well, we'll start here. The first thing we'll encounter is this 4 volt source, and we encounter it from the negative side, so we'll write that as a negative 4. Then we'll go and look at the drop across this resistor. That'll be 2,000 ohms times I1. And then the drop across this 4 kilo ohm resistor, that would be 4,000 ohms times I1 flowing in this direction minus I2 in that direction. There's I1 minus I2. And we'll be back so we can set that equal to 0. And then for our second loop with mesh current I2, let's start here. We'll look at the drop across the 4,000 ohm resistor that has a current flowing in this direction of I2 minus I1. So I'll write that as 4,000 times I2 minus I1. And then we encounter on the negative side this 18 volt source, so we'll subtract 18. And then we'll have a drop across this resistor, which would be 8,000 ohms times, well, the current flowing in this direction is I2 minus I3. So we can put an I2 here and then subtract I3, but I3 is negative 2 milliamps. So let me write that as negative 2 over 1,000. And we'll set that equal to 0. And then we do not need to write an equation for this third loop because we've already solved for I3. That is, I3 is negative 2 milliamps because of the presence of this current source. Well, let's take these two equations, rewrite those. Let's group all the terms that multiply I1. We have 2,000 plus 4,000. So that's 6,000 I1. And then we have a negative 4,000 I2. So we write that as minus 4,000 I2. And then the constant is negative 4 on this side. I'll move it to the other side. Set this equation equal to 4. For this equation, well, this was an I2. For this equation, we have negative 4,000 I1 and with I2 we have a 4,000 and an 8,000, so that's a 12,000 I2, and the constants will have a negative 18 and then 8,000 times negative and negative, that's a positive 2, that would be 16,000 divided by 1,000, so that's 16. So negative 18 plus 16 is negative 2. Take it to the other side and we'll have a positive 2. Now we can solve for I1 and I2. We've got two equations and two unknowns. Well, one way to do this is a fairly simple set of equations. We could multiply the top equation by 3 and add the 2. In that case we would have 18,000 I1 minus 4,000 I1. So that'd be 14,000 I1. We'd have negative 12,000 I2, positive 12,000 I2, that'd be 0. And we'd have a 12 plus 2 is 14. So we would determine that I1 is 1 milliamp. And then we could use either one of these equations. If we substitute for I1 here, we would have negative 4,000 times 1 milliamp. So that would be a negative 4. Take it to the other side, that would be a 6. 4 plus 2 is 6. So I2 would be 6 divided by 12,000, or 1/2 of a milliamp. And then I3, the third loop current, we solved for that right away earlier. That's negative 2 milliamps. And at that point, we could solve for any of the currents in this circuit. The current through this 2 kilo ohm resistor is I1, through this 4 is I1 minus I2, through this 8 is I2 minus I3. Well, let's take a look at this circuit that has two voltage sources, two resistors, and two current sources. Now, just as we've done with the other circuit, let's go ahead and write down expressions for our mesh currents. Let's define our mesh currents. We'll call the mesh current through this mesh I1 again. Let's call this one I2. And we'll call this one I3. Now once again, I3, a part of I3 flows through this wire that has the current source. So I3 is the current flowing in this direction through this wire, which is 2 milliamps flowing in the opposite direction. So once again, we'll say I3 is a negative 2 milliamps. Again, it's negative because the current is actually flowing in the opposite direction of the mesh current I3. Now, this current source, so this current source allowed us to define one of our mesh currents. This current source has two of our mesh currents involved. So this particular current flowing downward through this wire is I1 minus I2. But if we look at this, that gives us an equation that relates I1 to I2. So I1 minus I2, so the current flowing downward is I1 minus I2. And according to this current source, that's equal to 1/2 of a milliamp. So if we wanted to relate, say, I2 to I1, we could say that I2 is equal to I1 minus 1/2 of a milliamp. But let me write that. I'll just suppress the units here now and write that as 1 over 2,000. So now let's go back and look at our circuit. Now remember, when I3 was defined because of this current source, we didn't write a loop equation, a mesh equation for the mesh with current I3. We didn't need to because we'd already defined I3. Now, if we write an equation for the loop, the mesh loop defined by I1, we'll write this as minus 4 plus 2,000 times I1, and then we'll run into that problem we mentioned earlier. That is, how do we define a voltage drop across this current source? Likewise, if we wrote a mesh equation for the mesh loop I2, we could say minus 18 plus 8,000 times I2 minus I3, but once again we need to know this voltage drop across the current source. But rather than do that, here's what we'll do. We can write a loop equation by Kirchhoff's voltage law around any loop, any closed loop in this circuit. So how about if we think about this loop? This is a loop that includes both mesh currents I1 and I2. And we're picking those together so we can avoid now going through this current source. But anytime we see I2, for instance, we can write it in terms of I1, so this will actually be as though we're writing one giant mesh equation that really only depends on I1. Again, we're going around two meshes. One of them has the loop current I1, the other the loop current I2, but because I2 is I1 minus 1/2 of a milliamp, we can really go through this entire loop, and the mesh current, if you will the only mesh current we'll need is I1 as we move through it. Let's see what I mean by that. So let's start here. We'll go a -4. Then we're going to drop 2,000 times I1. So we'll add that. Then we'll come along and we'll see the negative side of an 18 volt source. So we'll write that as -18. Then we'll come through here and drop across an 8,000 ohm resistor, and that would be 8,000 times. Well, we'll have I2, but I2 is I1 minus 1 over 2,000. So that's I2 minus I3. But I3 is a -2 milliamps. So minus -2 milliamps, write that as a plus 2 over 1,000. That's our 2 milliamps. And that will proceed around and would be back to where we started, so we can set that equal to 0. Well, let's group the terms that depend on I1. So we have a 2,000 and an 8,000, so that's 10,000 I1, and then the constant terms, we have a -4, a -18, a -8,000 over 2,000, so that's a -4, and then a 16,000 over 1,000, so that's a +16. So we have a -4, a -18, a -4, and a +16, so that would give us a -10. Put it on the other side, and it's a +10. So that tells us that I1 is 1 milliamp. I2 Well, that's I1 minus a half a milliamp, so that's going to be 1/2 of a milliamp. And then I3 is negative 2 milliamps. And now again, we know the 3 loop currents. We could determine any current, and then once we know all of those currents, we could start to determine any of the voltages. So for instance, if we wanted to know this voltage, let's say we defined this node as our ground or reference, and we wanted to know this voltage V1 relative to ground, well, that would be 4 volts minus I1 times 2,000, and I1 is 1 milliamp times 2,000 ohms, that would be 1 volt, so V1, or excuse me, that would be 2 volts, so V1 would be 4 volts minus 2 volts, or 2 volts.